Okay, this will be our last video. We'll finish up our gravitation notes. 8, as you remember, is connected to 5, 6, and 7. What is the magnitude of the Earth's acceleration due to the force of gravity on it from the Sun? So again, we're going to assume that the only force acting on the Earth is the force of gravity between it and the Sun. We can actually calculate how the Earth accelerates due to this. The force of gravity between the Earth and the Sun, if you remember from question 5, what's actually, the actual situation is 3.53 times 10 to the 22nd newtons. The Earth's mass is 5.98 times 10 to the 24th kilograms. And we can solve for A. 3.53, 22, divided by 5.98, E24, and we get 0.0059 meters per second squared. And that might seem a little strange to you, because you're like, well, wait a second, those are both, that's a huge force, but take a look at the Earth's mass. It's even bigger than that force if you're just comparing the numbers, okay, because that's what we're doing here, we're comparing the numbers. So it kind of makes sense that the acceleration would be so small, and we haven't really gotten into talking about circular motion yet. That'll be in our next set of video notes. And when we get into talking about circular motion, we'll come back to what this acceleration would mean. Because very clearly, the Earth does not get pulled directly. It's not, getting closer and closer to the Sun as time goes on. Something else is happening here, but we'll come back to that later. 9, 10, and 11 are interesting questions, because you see this every once in a while. A spaceship is flying above an alien planet. The distance from the planet's surface to the spaceship is equal to the planet's radius. How much smaller is the gravitational attraction between the spaceship and the planet as it flies, as compared to the gravitational attraction between the spaceship and the planet if the planet is on the ground? So we're not given any numbers here. Okay, this is a conceptual question that is trying to determine if you understand how the force changes given changes to the distance between objects. We're going to have two examples here. Let's say here is your planet, here is your spaceship. It is on the surface. Okay, on surface. In this case, the distance between the centers of each object is just equal to the radius of the planet. So I would say that it's Fg equals G, m1, which can be the mass of, let's say, the spaceship, m2, mass of the planet, and r squared, where r is the radius of the planet. Now what happens when the rocket or the spaceship is flying? Something a little different. Not only is it one radius off of the surface, but it's also an extra radius from the center. So look what happened to the distance between the centers of the objects. It doubled. The mass didn't change, the universal gravitational constant didn't change. What changed was the distance of separation, where r1 is 2 times the original radius, where the original r, I keep saying radius, I should be saying distance between the centers. The original distance between the centers is simply the radius of the planet. That's why I keep mixing up radius. Now the distance between the centers is 2r, because it says that the spaceship is flying at a height above the surface of the planet. That's the height that it's flying above the surface of the planet is equal to 1 planetary radii. So we change r1 to 2r. We're going to square that. We end up with g m1 m2 over 4r squared. So this is 1/4 of the original. In other words, the force of gravity is 1/4 as big. Now, this is an important question. The reason that we talk about this is because it gets at the difference it gets at what the real meaning of r is. Remember, you have to understand that r is not simply just some radius. It's the distance between these centers. even though the objects were touching here, the centers were 1 planetary radii apart. Here, even though the spaceship is 1 radii off the surface, it's 2 radii from the center of the planet, and that is what matters. We have some similar questions for 10 and 11. If an astronaut on the ground has a weight of 800 newtons, what is his weight when he is 3 Earth radii away from the center of Earth? So here's what we're going to do. Okay, here's our astronaut. We know that for this case, Fg equals g m1 m2 over r squared. And we know that since we're talking about the force of gravity on the astronaut, that's the same thing as his weight, so Fg must be equal to 800 newtons. When he's 3 Earth radii away, oh wait, hold on a sec. When he's 3 Earth radii away from the center of Earth, that means 1, 2, 3. That's 3 Earth radii away from the center. Here he is. Okay? Remember that when he's on the ground, they are 1 radius apart. 1 Earth radius apart. Now, he's 3 Earth radii away from the center. So Fg1, we'll say, is gm1 m2 over r squared, or r1 squared. R1 is equal to 3 times r, which means this is g m1 m2 over 3r, all that squared. When we square 3r, we end up with 9r squared. So that tells me that Fg1 is equal to 1/9 of the original. Since the original was 800, 1/9 of 800 newtons is 800 divided by 9. Fg1 is 88.89 newtons. And that makes sense. He got farther away from Earth, so the force of gravity decreased. Okay, his weight is less than it was. 11, at first glance, looks exactly the same. What is the astronaut's weight when he is 3 Earth radii away from the surface of Earth? But notice what it says. It says 3 Earth radii away from the surface. How far is this astronaut from the surface? 2 Earth radii. So we're talking about this situation. 1 away from the surface, 2 away from the surface, 3 away from the surface. We call it R2 this time, is 4 times the original R. If you take 4r and square it, you end up with 16r squared. So Fg2 is equal to 1/16 the original. If the original was 800 newtons, 1/16 of that is 800 divided by 16. Whoa. 800 divided by 16, and we get 50 newtons. Okay, makes sense that the person is now farther out, the force of gravity on them is even less. Last example is another algebraic one. The force of gravity between 2 stars in a binary star system, these are 2 stars that actually orbit each other, is F. In terms of F, what would the force between the stars be if both doubled in mass and the distance between them tripled? So, the original force, it says, is F. And we know we're talking about the force of gravity. So we're just going to write this. F equals G m1 m2 over r squared. Then we want to know what happens to the force when we do all these changes. So I'm going to call that F1. G is not going to change. We're doubling both of these stars. So we have M1, 1, and M2, 1. And again, you can use A if you want. You can use a little star. You can use whatever, okay? I just chose to use 1, and I guess maybe that's a little confusing. But these just indicate that we're dealing with something a little different here. And we're even dealing with a new distance between the centers. Let's see here. We're told that G is going to be the same. The new mass for the first star is 2m1. It's twice as big. The second one also twice as big. And the distance between them tripled, so R1 is now 3R. So we have F1 equals 2 times 2 is 4. We're going to pull that to the front, so 4G M1 M2. 3R squared is 9R squared. This is just my original force. So I have F1, the new force, is 4/9 the original force. So sometimes you will have questions where you have to do kind of this compound reasoning and reasoning through a couple different changes. Okay? I know the algebra stuff can be where this gets trickiest, but it's just like anything else. The more you practice it, the more you see it, the more familiar it will get to you. I'm going to stop this video here. Our next set of videos will be on circular motion, which ties in very nicely with gravitation. I will talk to you later for those. Bye.